Okay, so finishing the picture here, we add everything TensorFlow needs to know to solve our problem. We define loss, which again is synonymous with error, using sparse categorical cross-entropy, which is a solver which, so the solver function in this case punishes especially bad choices and forces more stark choices, which cause our classification system to ultimately be more decisive about discarding weak candidates. More on that in a minute. There are others, and again, picking a whole bunch of different ones is beyond the scope here, but you can dig into the documentation in the hands-on and try what you like. But for categorization, that works pretty well. The optimizer we'll use in this attempt performs gradient descent with an adaptive time step and momentum. Which we think will be an improvement over the standard stochastic gradient descent. So time step is designed to make you be able to move through the descent through your graph quicker, and momentum is going to help you to avoid getting stuck in little local minimum wells. We're going to monitor our accuracy as we go to keep tabs on how it's working out. Okay. Defining error is the key to obtaining a solution. Domain knowledge becomes really important in determining what sort of error is acceptable. And cross-entropy loss is excellent for categorization problems. Dive into all of them again beyond the scope here, but you might find that your particular problem is better served by a different method of calculating the error. Okay, here we see some examples of how this this sort of work is working, and GPT-4 is easy to grade quite literally. It's passing all of these real tests. Okay. Here's some images and output generated by GPT-4 or Stable Diffusion. And one of the more interesting things about these is that these were completely emergent capabilities that really weren't expected by the people that were creating it. So let's go back to our discussion briefly in our about clustering and overfitting. So you might remember that graph from the clustering discussion a little while back, where it just flattens out and you've got entries that that have almost no error, but it turns out just don't give us any useful information. And we want to remember that we want to stay on, on the cusp of that, so that we get the most useful information and not necessarily the best fitting information. So just because you fit something does not mean you're seeing the real picture. So here we've got this curve, okay, but we might find that this fits it extremely well. And if we're going into too high of a dimensionality, we're trying to be too clever, we end up fooling ourselves into believing we've got a more complicated picture than we really have. When we add some more points in, we find that, hey, actually it was never that complicated to start with. So one solution is to keep using higher order terms, but penalize them. And these regularization hyperparameters enable our solution to have good generalization, and will show up again in our workshop and throughout your machine learning endeavors. It's like an Occam's razor for machine learning. Cross-entropy, why it's good for categorization? Well, because it greatly penalizes bad guesses, but it leaves relatively unlikely results intact. One of the things that these algorithms do is they sort of rate how surprising the result is that comes out of these collections of neurons. And the point of this would be to clear the field of what seem to be extremely surprising results, like that a 1, could that really be an 8? That seems unlikely. But it allows for cases of genuine confusion, like on all of my checks. Is it a 9 or a 4? It's a good thing we write it on, in words as well as numbers, because sometimes it can be hard to tell. Let's talk about training. So we're going to do some more introspection here, and we can track the error as the run progresses that we plot it. Nope. Sorry, there's supposed to be an animation there that's not. In any case, we're training the data here. We're taking the images, we're going to run them for 40 epochs, and we're going to let the neural net work out what values give them the best chance of finding the truth about the nature of these images. Here we see some of the results. We go through all 40 epochs and see results like this. And we can see that there is a little bit of overfitting. We've got some pretty perfect fitting to the training data, but less accuracy in the validation data, and you can see that in the output there. Validation accuracy is at 97, but the accuracy on the training data was up to 9999, which is, that disconnect is something we're going to get rid of. We're going to find that the training data pretty quickly gets to a plateau lower, and that plateau point is where the model's learning learning effectively ends. Okay, and we're going to have some curves here that plot out how those are. And don't worry about the fact that the orange line kind of crosses the blue line there. That's because the results are aggregated and does not actually mean that we had, pre-knowledge or something. Okay. So loss is the mathematical value we've specified in our model for our parameter fitting. Accuracy is simply how many we get right. When we test our model as an application, it might not apply to non-classification problems, and it doesn't capture how much is right or wrong, but it's useful for categorization problems, for sure. The two are normally closely related and track each other, and we'll choose accuracy for our graphs, and any user understands what accuracy represents. Okay. So, okay, this just discusses that. That's fine. So. More neurons here. Let's try making a wider one. We're going to start playing with the hyperparameters here. Instead of 64, we're going to go 512 and see what happens. Okay, we improved from 96 to 98%. That's pretty good. More parameters also equals more time to train, but it converges sooner. So total runtime isn't always the thing that you want to be the most afraid of, especially when you can identify, where those plateaus are and where, where you can start getting, or where you stop getting more useful training out of it. In Keras, the non-trainable parameters are the ones that are not trained using gradient descent for things like pre-made filters, pre-trained sections, statistics things like update for Barch norm using mean and variance. So if those things are important for your particular problem, then gradient descent might not work the way that you expect it to. So let's see. We got quite a few more trainable parameters. So we went from 50,000 up to about 700,000, which means that we did a lot more work to get this, but we did get an improvement. So maybe we go deeper. Maybe we just add more layers and see what happens. And I'm going to give you a preview of the answer of this, which is that just brute forcing your way through a problem is going to give you bad results in neural networks. So you can't always just throw resources. You can't throw compute time. You can't just chew on something longer or harder or deeper and expect to get certainly not linear results, and definitely, and sometimes not even better results at all. Sometimes much worse, and sometimes nonsense results like the overfitting that we get. So when we go deeper, we're going to see that sometimes we run into vanishing gradient problems. We run into all kinds of problems, but let's try and we'll see. So in this case, we're just going to add one more layer and keep the 512 neurons in order to see how that goes. And it turns out that we lost a little bit of accuracy going deeper. Wider turns out to be the winner in our quick experiment here. And let's see, here's the final ratings. Yay. 98.2 is the best that we could do for our character recognition. Okay, and brute force again. You can't brute force your way to success. Time and memory costs are, ultimately those things are finite, and you run into overfitting, you run into vanishing gradients. We have to be a little smarter than just being bigger and better. Okay. So I believe, we'll go a little farther here. So let's talk about image recognition done in even better than we've been discussing. So this is a diagram of the stack of the AlexNet, which won the 2012 ImageNet LSVRC, which changed the deep learning world. And this one applied convolutional neural networks. Convolutions let us filter images to transform them, and different filters will identify different aspects that allow us to improve image recognition. We give each neuron a peek at only a little part of the data, and it might be surprising that that actually turns out to enhance the overall output. If we're letting it consider separately each individual part. And in this one, we can see that we're padding the edges with zeros so we can consider the corners, and often the edges turn out to be very interesting for this kind of work. We don't have to necessarily get every single square. We can do some stepping. Oh, this is not advancing. There we go. Okay. Yes, convolutions. Okay, we're taking a subset and letting each neuron chew on just a subset instead of the whole image at once. And that turns out to have advantages. So old school algorithms used handmade convolutions for filtering like this. Neural nets do it for us even better. We iterate and learn the convolutions as we go. So we had these edge detector algorithms, which were pretty simple and could just figure out where the edges of images were. If you ever played with early Photoshop, you probably did this a million times. Convolutions will detect relationships between adjacent nodes in a way that our flattened image processing just couldn't. And it helps us out in two-dimensional images, but it can continue working into higher dimensions as well. The initial layers catch gross details like edges, and later layers can start to pick up more subtle details, building on the work done by earlier layers, and start to detect shapes, styles, etc. Okay, here we have a demo. We have this image, and we're going to learn from it. Well, we don't always get great results. So. Filters progressively scan over portions of an image. We're constrained by the input to have 3 filters. And convolutions can be thought of as scanning across the image or applied simultaneously in parallel using shared weights. If you have the parallel computing power, as we might in a GPU, we can be even more parallel, and if we don't, we have to do more serial scanning, but we can get to the same result one way or another, maybe with a little more time. Okay, looking at different parts of the convolution. Now, the spatial extent is the size of the filter. The stride lets us skip pixels, and padding lets us focus on the edges and the corners. So those are all hyperparameters that can be adjusted for your convolutional networks. And the zoomed out view is done by pooling as we progress through the layers and giving us the top level view. A pool out can be done in a few different ways, and we can use the average of a collection of pixels, but max pooling turns out to be more effective, and that takes the most interesting feature, and it's also a bit cheaper. So filters are going to be visualized here with stacked RBG. So color specialization is where they aren't proportional. For instance, they're gray, and we're going to see different representations of each portion of it. And each individual neuron there kind of looks like nonsense, but each one of them holds an important part of the image that is being used to discover an aspect of it. And when they're put together later, it's going to make sense and actually going to give us some surprisingly good results. So we don't need to stretch out the image right now. The convolution requires 2D inputs. The first layer is convolutional 2D. 32 nodes is a hyperparameter we can tweak. We could do a different number. We can look around for good starting points. Since we're not doing the whole image, we can pick how big we want our convolution to be. Same for 3x3 filters. And then we can use a max pooling layer to find the interesting parts and flatten that output out. So we try this with a convolutional network. We get even better results. We end up with 5,000 parameters, and we get a much better accuracy of 98% there, 98.7 or 0.987. So we're already beating our best effort with the regular neural network. We add another convolution layer, and let's see if it gets any better. And we've gotten considerably better. We almost doubled the total parameters involved, but the validation accuracy is up over 99%, arguably even superhuman. Okay. So when we do overfitting, when we get to the point where we stop learning, but we keep making the accuracy on the training data go up, that's a hint that we're overfitting. Okay, and that in that case, we're just memorizing basically what these specific images in the training set look like instead of learning about their aspects and being able to apply them against a training set. So we've got this disparate gap between the training and the testing, and that the degree to which there's that gap is really the degree to which you've overfit. Okay. Finally, I want to mention convolutional networks with dropout. I'm not going to go a lot into why we do them, and in fact, to me, and I think to a lot of people, it's surprising that it makes a big difference. But if you just drop out a portion of the neurons at different times, just basically completely discount them, first 25% and then 50%, it turns out that it can pretty dramatically improve how your network trains. It's not used in the final trained network. And in fact, it's disabled during testing here, but it turns out that during the training, you can get surprisingly good results by just basically blinding half of the neurons at a time. And that dramatically closed this gap for overtraining here. We're up to 99.2% accurate, okay, just from playing with these hyperparameters and adding some functions. Okay. Batch normalization. We can normalize results between layers this way and improve results by avoiding vanishing and exploding gradients. There's a bit of a live controversy about when and how to optimally apply this method, but it's easy to test it out, and that will be left as an exercise. I'm going to try it out here, and we get pretty good results. We're a little bit under 99% again, though, but we're still looking good and not much overfitting there. So, okay. This is going to be the last thing I do here, I think, and then we're going to step out for our break. So this is a demo that lets you see the backpropagation in real time and lets you see, in particular, where each neuron got each thing and how it ends up leading into the ultimate image that you're going to have. So let me see if I can find. Okay. So for this demo, I'm going to draw a number. What number should I draw? Someone shout out a number. 7. 7's our number for today. There's a 7. Okay. So this is how it interpreted the pixels. Okay. And each of these represents a neuron in one of the networks, and it's pulling convolutionally some portion of that data. And then we're doing another layer that's pulling from the one before it, and so on until we flatten it out. And then in this final layer, and then we get this telling us that it's a 7. It's decided based on the output that 7 is the most likely outcome. So let's see, 7 is the first guess and 4 is the second guess, but that seems pretty unlikely. Okay, I'll try another number here, maybe a 2. A very bad 2, how about that? See how it does. Okay. All right. Okay, and there's an image of what that looks like. Okay, and this is what the hands-on exercise is going to be for deep learning for this afternoon, which is to use the MNIST fashion set. And we're going to do the same kind of thing. We're going to play with the parameters and see if we can't get them any better. But I think it's time now for us to open up the floor to any questions and then maybe get some coffee and take a break, and we'll come back with some hands-on for this afternoon. So any questions before we... I think the question was, is there a strategy for setting the number of neurons in your convolutional network with respect to the output? Fully connected layer. The answer is I don't know. is really my answer. And the goal of what I'm trying to convey here today is just that you're going to be able to experiment and find the different approaches are going to give you different results, and some will be better and some are worse, and that there's actually no, there's no great predefined rules for any of this. So the nice thing about the hands-on exercise is that you'll have the opportunity to try creating these kind of networks and see what works for you. Let me see if I can recapture. It's a little hard to hear. I think you're saying you're asking if we want to do reducing the dimensionality before we feed it to the neural network. Yeah, I mean yes. There's obviously different techniques for doing these things, and neural networks are one of the techniques for achieving this. Sometimes you have a problem that serves itself well to reducing the dimensionality, so you're feeding something simpler to the neural network. And again, one of the things that has been apparent to me in the reading I've done about this is that you might think that the best way to do it is to put things in a certain order, and there might be a best way. There's some ways that we found heuristically, often work well. So, for instance, for categorization, we're going to do a particular type of solver, et cetera. But there's no guarantee that that's going to end up being the best in any case. That said, I do think it's a win usually when you can do something that reduces the size of your input, and still give you useful information. So I think the answer to that is certainly yes. And when you're trying to compress down massive data sets and trying to reduce massive computations, then everywhere you can shave off a bit of data without losing information is definitely a win. All right, well, I thank you very much, and I hope to see you for some PySpark exercises and some deep learning exercises this afternoon. Thank you.